Hi everyone. In this talk, I'm going to present the paper Gradual DRAM and Secure Computation for RAM programs. And this is a joint work with Lilintal. So secure multi-party computation is a tool that allows a set of parties to directly communicate while obtaining the same security guarantees as when given an access to a trusted party that computes the function. Specifically, any adversary that corrupts a subset of parties cannot learn anything beyond the output of the computation. Security is proven in the presence of two central types of attackers. A passive adversary, which is a benign, semi-honest attacker that follows the protocol's instructions while trying to violate privacy. Whereas the strongest and most realistic attack scenario is an active or malicious adversary that can follow an arbitrary attack strategy. Another aspect of defining security is the number of corrupted parties. In the honest majority setting, the adversary may corrupt less than half of the parties, whereas in the dishonest majority setting, all parties but one may be corrupted. And working in this model has the advantage that the party does not need to trust anyone but itself. By now, we know that MPC is very useful and has many important applications, such as private electronic voting and auctions, privacy-preserving data mining, protecting cryptographic keys, and many more. In this talk, I will focus on the two-party setting and discuss passive security, where active security can be amplified based on known techniques. Most of the research for secure two-party computation has been performed for Boolean circuits and does not handle efficiently accesses to a large memory, which is translated into a linear scan of the memory inside the circuit. Now, this translation causes a huge blow-up in the description of the circuit. Also, most applications in practice today are more efficiently captured using random access memory or RAM programs that allow constant time memory lookup and contain branches, recursions, and loops. The RAM model covers many important algorithms, such as graph algorithms, for instance, like Dijkstra's shortest path algorithm, binary search on sorted data, finding the kth rank element, stable matching, and many more. The generic transformation for RAM programs that run in time t implies circuits of size t cube, which are non-scalable even for relatively small memory sizes. Now, to address these limitations, secure protocols have been designed directly in the RAM model, and such protocols require additional mechanisms to maintain the memory. So let me start by explaining about the RAM model. In this model, we have a remote CPU or a client with a small storage that is modeled as a program P that is given an input X and is accessing a physical RAM or a server with a large storage capacity. Note that the running time of the program is typically much smaller than the size of the memory. It could be even at the polylogarithmic scale. Now, the access pattern to the RAM includes the locations in the memory, the type of operations, and the value to be written in these positions. As shown by Goldreich and Ostrowski, the access pattern may leak information about the stored data, and you would like to protect it, in addition to protecting the stored memory from an outside observer. So Oblivious RAM is a tool that supports dynamic memory access while preventing any leakage from the memory. Namely, ORAM is a technique for hiding all the information about the memory of a RAM program, including both the content of the memory and the access pattern to it. ORAM algorithms take a program P and a memory D and compile them into a new program and memory that support obliviousness while preserving correctness. Their overhead is measured with the blow up in the size of the compiled program and memory, as well as the number of memory accesses to the compiled memory per single access to the original memory. In particular, the efficiency of ORAM constructions is evaluated by their bandwidth and storage blowups, where the former refers to the number of data blocks that are sent between the parties per memory access, and later refers to the multiplicative overhead of the oblivious memory size. Ever since the seminal work by Goldreich and Ostrovsky, a large sequence of works improved the different parameters of ORAM. And here are just a few examples. There are many, many interesting and important works in this area. Recent constructions also incur practical polylogarithmic overheads in the size of the memory. In secure computation for RAM programs, both parties have input for the computation of the program, which they mutually run while updating the memory on the fly. Therefore, any secure protocol must address the memory accesses as well. Now, without loss of generality, we can think of the memory being initially empty and occupied on the fly. So starting with a sequence of small CPU steps that define a program, each such circuit updates the state of the program and computes the next read or write operation based on that, as well as the value to be stored in the memory. And these small CPU circuits can be garbled using the classic garble circuits approach. So in order to hide the access pattern to the memory, all prior secure schemes are built on top of ORAMs. And similarly to the domain of MPC for circuits, previous schemes of MPC for RAM programs follow one of the two approaches, either based on garbled circuits or secret sharing mechanisms. Where constant RAM solutions employs an object called garbled RAM or GRAM, which extends the notion of garbled circuits for Boolean circuits to support RAM programs. As in the distributed setting, the memory is initialized empty, and therefore it makes no sense to initially run the garbled memory algorithm, has done all prior work. Another drawback is regarding the security amplification from semi-honest to malicious, which requires using zero-knowledge proofs for highly complicated statements or running a distributed protocol for the memory initialization. Finally, the security analysis of this construction had proven relatively to a weaker, unprotected memory access notion, or UMA, where the attacker may learn the initial contents of the memory D as well as the complete memory access pattern throughout the computation. A transformation from any DRAM scheme with UMA security into one with full security is based on ORAM, which adds another layer of complication to the scheme. So as I mentioned earlier, garbled RAM is an object that is analog to garbled circuits, but is defined for RAM programs. Meaning GRAM is defined based on three algorithms: one that garbles the memory D into D tilde, a second that garbles the program P into P tilde, and a third that encodes the input X into X tilde such that only the outcome of P of X when accessing D is revealed from these encodings. Also, the garbled memory and input sizes do not grow beyond a polylogarithmic factor compared to their original values. And it's important to note that at the heart of every GRAM construction lies a mechanism that prevents the evaluator from rolling back and evaluate the CPU circuits on an older version of the data elements. Therefore, memory garbling algorithms must be embedded with authenticating tools, even in the semi-honest setting, which complicates this problem compared to garbled circuits. Finally, I want to say that as for Boolean circuits, combining GRAM with passive oblivious transfer implies passive 2PC for round programs. Well, amplifying security to the active setting is harder than for Boolean circuits, since proving the correctness of the garbled memory is much more challenging. So motivated by the previous discussion and the fact that all GRAM constructions are based on binary trees, we begin by exploring tree-based ORAM constructions and explore the flexible notion of gradual ORAM. So this notion is an extension of the classic notion of ORAM that does not require an initialization phase to compile data. Instead, a new algorithm is considered that handles the memory insertions separately and can be skipped directly to the run program set of instructions. An immediate advantage that is implied by the flexibility of the gradual ORAM is resizability, where the dependence on a fixed size tree is removed, allowing for flexible storage. And I like to stress that this concept is not new and has been suggested implicitly in prior work. So next, we extend the notion of GRAM and consider an analog gradual GRAM notion with no memory garbling algorithm, meaning that this object is defined by only two algorithms for garbling the program and the input, where all the memory operations are incorporated within the program. And this modification implies that the garbling mechanism is now only involved with a sequence of small CPU steps that are garbled using the classic garbled circuits approach. Therefore, it is conceptually closer to the analog garbling mechanism for Boolean circuits. There are several important advantages when employing gradual RAM. For a start, this new concept enjoys all the advancement of garbled circuits, such as half gates and free XOR. Most of the work can be shifted to the offline phase, meaning before the input to the computation is even known. Also, security can be more easily amplified to the active settings, since we can borrow tools from for correctness that have been developed for Boolean circuits. And finally, the space complexity of the prover can be made minimal by processing one step circuit at a time. So we next revisit the GRAM construction from class Gradual and improve it in 2 dimensions. We first proved that it can be combined directly with tree-based ORAMs, where the best matches are with simple ORAM and circuit ORAM due to their root-to-leaf eviction algorithms. We observed that some ORAM constructions, or for some of them, it is beneficial to build a combined tree that contains both the ORAM buckets as well as the GRAM information, and is proven directly secure rather than via UMA. Other ideas can also be applied to other other GRAM constructions. So in this construction, each internal node is associated with a PRF key that is encrypted under a PRF key that is associated with the parent node. And each memory access is translated into a sequence of D navigation circuits, where D is the depth of the class tree, and a step circuit that carries out the run program instruction. So during the evaluation, each navigation circuit outputs a translation mapping that allows the evaluator to learn the input label for the next node. Either it's left or it's right child, based on the path to the read position in the memory. In addition, the circuit refreshes the PRF key that is associated with each node that is traversed and computes a new set of PRF values based on the new key to be stored on that node. So the step circuit finally performs the read or write operations at the leaf level. So we recall that the gloss tree is built on top of an oram tree, so as illustrated here, meaning that at first the oram is constructed assuming that we use a tree oram. Then the tree is viewed as a long array, where the gloss tree is built on top of it, treating each entry in the oram tree as a leaf in the gloss tree. So we observed that gloss can be made consistent with our notion of gradual GRAM, where the combined tree is built on the fly based on gradual oram. This requires adjusting the GRAM algorithms to support an incomplete tree while maintaining authentication. Also, it allows to avoid expensive initialization phase and saves on the space resources, as the size of the tree is minimized rather than growing with the maximum size of data. So maximum potential size of data. So finally, note that due to the conceptual similarity to the gobble circuit approach for Boolean circuit, our approach is also easily extendable to the multivariate setting by applying common distributed gobbling approaches to the gradual GRAM functionality. And these protocols will potentially scale much better than when running a distributed protocol for implementing the gobbled memory algorithm, as done in all our work. In order to understand the qualitative differences between our gradual GRAM construction and gloss, we compare the number of nodes visited in the garbled memory in both cases and the sizes of the garbled circuits involved on a single oram access. So combining the oram tree with the GRAM tree enables to eliminate a factor of log n in the overhead, where n is the number of memory entries. So let me conclude by saying that the efficiency of MPC for RAM programs is not yet understood as it is for MPC for circuits, and much work can be done in pushing these protocols into the practical regime. Thank you for listening.